This presentation will be live broadcast, and at the end of the presentation, we have a Twitter stream and also a live chat. We have two students sitting here. Raise your hand, Jaysha and Brandon, who will let us know about the Twitter and also the live stream chat. Also, for those who are in the audience, because this is being live broadcast, if you'd like to send in a question at the end of the presentation, for Twitter it's hashtag UMCOE, and for live stream you go to coe.miami.edu/speaker to do a live stream chat. You can submit questions either way. So at this point I'd like to thank Dr. Sirignano for coming here from California. Thank you so much for taking the time to visit with us. And Dr. Rajat, can you introduce
Okay, I would just have a brief introduction to Dr. Sirignano. First, thank you very much for visiting us. We have honor for Dr. Sirignano to visit us, give us looks like a very exciting talk. I'll briefly talk about his background. He's a professor of mechanical workspace engineering and Henry Samuel Endowed Chair in Engineering at the University of California, Irvine. He was the George Thelman-led professor and department head at Carnegie Mellon University from 1979 to 1984. And before becoming the engineering dean at UCLA, Dr. Sirignano was a professor at Princeton University from 1967 to 1979 after receiving his PhD from Princeton. There are many other honors, and I will just skip it here and you can read Dr. Sirignano.
Thank you. Well, thank you for the very kind invitation, and thank you for the kind introduction as well. I'm very pleased to be here. It is an honor, and I've met some very interesting people here and learned about some very interesting work. Now, when I was first informally told by Professor Dan Berg that I would be invited here, and he said it would be a general audience more than mechanical and aerospace engineers, I tried to think of as general a topic as something which is something I knew something about. And I remember about 20 years ago when I was on an advisory panel for NASA, and at that time someone named Dan Golden, Dr. Dan Golden was the director of NASA, and I was in a conference room with him where he said, and I don't know if this is true, I didn't get the facts, but never let the truth get in the way of a good story. But what he did say was that the things that, scientific subjects that interested most of the general public were spaceflight and dinosaurs. Now, my 6-year-old grandson probably knows more about dinosaurs than I do, so I decided I should talk a little bit about spaceflight and a fairly narrow topic within spaceflight having to do with rocket combustion. And in particular, it's a problem that has plagued the development of rocket engines, especially liquid-propellant rocket engines, but other rocket engines as well, is something called combustion instability. And I was a teenager at the time of Sputnik, and that turned me on, so to speak. I wanted to not only be an aeronautical engineer, but I wanted to get into rocket propulsion. And what I've learned over the years is that one has to look for opportunities. Now, the Chinese come from a very ancient civilization, and what we faced when Sputnik went up was a crisis. And by the way, the Chinese writing I was helped by Professor Fang Lu, who some of you may know from UCI. But I'm told that the Chinese symbol for crisis is the sum of two symbols. One is danger, and the other is opportunity. And for me, it was an opportunity that guided me through a lifetime. So the advice I have and by the way, this is a Soviet postage stamp. They were very proud of Sputnik, obviously, and they should be. But the advice I have for young people is you don't have to make a crisis. It's easy enough to find one. But when you find it, look for the opportunity in the crisis. There might be something for you in that. So that's a word to the young that may benefit them sometime, and I thought I'd add it in. Well, the particular challenge that I have worked on and has plagued the rocket development, especially, as I said, liquid propellants, is combustion instability. And it's a problem that doesn't go away. This is a sketch of the F-1 rocket. 5 of these were the lower level launch stage for the Apollo mission during the 1960s. And that was what I was introduced to as a graduate student. And the reason it doesn't go away is that any chamber which is confined or partially confined and filled with gases has acoustic resonant frequencies. And the rocket chamber, therefore, is a cousin of a musical instrument. It has an infinity of resonant frequencies. And when you have combustion going on, if the timing is right, the combustion process can drive the oscillation, and the amplitudes can be huge. More than 100 atmospheres amplitude are possible. And what happens when you have hot gases with large amplitude oscillations is that places like the nozzle throat, with the flow coming out here, already your mass flow per cross-sectional area is high, and you're already protecting as much as you can for heat transfer, but the heat transfer under oscillation is greater than heat transfer in steady flow. Some of you take heat transfer courses will have perhaps realized that. So that's one place it can burn out. The other is the combustion becomes so efficient that it comes close to the, instead of needing the whole chamber, it comes closer to the injector face. This is where they're injecting out the propellants, all these little holes, and it can burn out the injector. And this was an issue on the F-1. The F-1 solved this partially by putting in these baffles, which would protect against transverse oscillations, which were the dominant and most dangerous kind. So this problem is something that faces the development of all liquid propellant rockets. And 50 years after Apollo, there's still interest in this from the Air Force, and in fact, they're funding me on the subject. Now, let's see, this should, okay. There are various kinds of oscillations. Longitudinal mode, make sure I get, okay. These are, the X direction is the main flow direction of the nozzle, and these represent pressure and velocity. And you can see that they're oscillating, and for this, it's a standing mode in the longitudinal mode, and so they're out of phase, pressure and velocity. So where you have a node for one, you have an anti-node for the other. A node means it's not oscillating locally. These are nodes. Where it's oscillating the most are anti-nodes. But there are tangential modes, which are the ones I'll focus on. And this is a standing tangential mode. These show pressure profiles where it's basically sloshing back and forth. You see the red is the high, blue is low, it's changing direction. But you also get spinning waves where the wave moves around. In a linearized theory, the standing mode is the sum of two opposed spinning modes. And then it's also possible to get radial modes this way, where it sloshes in and out radially. We're going to talk about these two primarily, and these just show schematically the different modes, the directions of velocity as it sloshes. These are all the first tangential here. If you get the second tangential, this breaks up into finer parts, and these are radial modes, which you can get the second radial as well. We'll talk mostly about the first tangential mode. Oh, I'm pushing the wrong one. Okay, I'm sorry. Got to get used to that. Okay, now just to focus a little more, it's been known for a long time that you can trigger the oscillation. This means, well, there are three kinds of stability zones in a parameter space. One is where it's unconditionally unstable. No matter how small your disturbance is, it will grow. Unconditionally unstable, you'll get an oscillation. The other end is it's unconditionally stable. No matter how much you bang it, the bang will decay, so to speak, and you go back to a steady state. In between, there's what can be called either conditionally stable or conditionally unstable. You have to exceed some threshold in order to get it to grow. So, for example, and the way they did this in the rocket industry was actually they put in gunpowder in shells and burst it. They called it bombs, little bombs. And this shows mixture ratio, the ratio of oxidizer to fuel here. And that might be varied. And these are 4 different levels where you have increasing number of grains of gunpowder and increasing strength of the burst disk on the little shell where the gunpowder is. And then this is burst. And what you can see out here is that here's a region where it's unconditionally stable. Here's a region where it's unconditionally unstable. It'll always grow. But in here, you have to go above some threshold in order to get it be unstable. And we're going to focus mostly on this regime because this is where the interest is. Basically, the engine will be most unstable in the regions where the performance would be highest. So you're trying to get as close to this as possible. You don't, if you go way out here, it's safe, but it's low performance. That was a back. Oops. There. That shows I was there. Okay. Now we get a little more mathematical. First, I want to talk about nonlinear dynamics, which this is just to get some of the ideas across. This does not describe mathematically the behavior itself, but it gives you some of the issues that we're facing. You've seen differential equations. These are ordinary. We're actually going to be working with partial differential equation. Here's a simple linear oscillator equation, mass on a spring, or certain kinds of electrical circuits. We put damping in it. This is still a linear equation. Now here's an equation which, essentially, if you think of this as a restoring force on the spring, this becomes nonlinear, has a nonlinear restoring force here. Here's now starting to get more interesting. This has damping just like this term, but here if K is positive, this is a damping term. Here, if K is positive, for low amplitudes where this dx dt squared is smaller than 1, this is also damping. But if you get a large enough oscillation, this changes sign, this term, and actually becomes driving. And that's the kind of thing that can happen with combustion instability and triggering. And these are just more complicated here, adding more nonlinearities. But down here, this damping term becomes more interesting and now becomes a little closer to the rocket engine because it's no longer what's happening at that instant in time, but there's a history effect. It goes back a time tau. So basically there's a history effect in determining it, and that represents in the combustion process what's happening during a sequence of processes before you actually release your energy. And that gets affected as well. So here's like the first equation, just get circles. Here, if you put in damping, you decay. Here's a case where you will, above this threshold, you will grow, like this equation. Below it, you decay. And here's a case which is even more complicated, where you, actually it's more like this one, where it changes sign more than once. You can have a threshold above which it grows, and then you have a stable limit cycle out here. So, without going through the derivation, which would bore you, we basically have equations for conservation of mass, momentum, and energy, and we simplify the problem by integrating over the flow direction and reduce it to a two-dimensional problem for the moment over the two transverse directions. And we get, from our equations, a wave equation. You'll see things that look like the wave operator, the Laplacian in cylindrical coordinates here of pressure P, second time derivative, minus sign here. This is a damping term that comes from the nozzle primarily, could come from the injector too. And then you have a lot of nonlinear terms that come from the nonlinear gas dynamics, but you have this term that comes from the combustion process. E is the rate of energy released per unit volume. Energy per unit time per unit volume is E. And the first derivative of that will appear. This equation comes from combining the equation for conservation of mass and the momentum equation, so you can think of it as replacing conservation of mass. And these are two momentum equations. Now, on the large scale of the chamber, we neglect the effects of heat conduction and viscosity because those depend on gradients, and we're working on the large scale, but we will, on a multi-scale problem later, we will talk about that. So this is the equation that's governing us. And my collaborators here are Professor Sedaris, who's really an expert in systems engineering and operations research. And when we get into some of the statistical analysis, he's been very helpful. Pavel Popov is a postdoc. Jeremy Krug is now left. He was a student, master's student. Mittat Burkhan of the AFOSR is sponsoring our work. And we're trying to develop simplified numerical models. And basically what we're doing is analyzing the instability once there's a disturbance as a deterministic process. But the disturbance itself is random. It means something happened you didn't want to happen. And we're treating that as stochastic. So there's a stochastic triggering, and then after that, it behaves deterministically. So we can do our statistical analysis on that. And we're also identifying various triggering mechanisms and looking a little bit into the potential for control of these phenomena. And we'll talk a little bit about that, time allowing. All right. Now, this is now looking at the injector face. We're doing a simple analysis. We can take n injectors. We're taking 10 here, 1 in the center, 3 in an inner ring, and 6 more in the outer ring. So these are co-axial injectors. You have oxygen coming through the center and fuel on the outside. That's the standard because you want to shelter the oxygen from reaching the walls in this hot environment. It can obviously do some oxidation if you do that. So that's the standard. And we're saying that we have a 28 centimeter diameter chamber with we're operating at 200 atmospheres, and the mean temperature of the products are 2000 Kelvin. All right, now I should say, in addition to the chamber equations, which are on this scale, we're doing an analysis for the mixing and combustion on a scale for each of these injectors. So what we're actually, and then we couple that to the outer equation. So we're doing n plus 1, if n is the number of injectors, we're doing n plus 1 coupled calculations, each involving several partial differential equations. And what happens is that the pressure and velocity from the chamber affect the rate at which mixing and burning occur. And the rate at which mixing and burning occur affect that E term that I mentioned in the wave equation. So it's coupled that way. Actually, if we, in some cases that I'll briefly talk about, we also couple in the acoustics that are upstream in the ejector, going back into the injector, And those would involve still more equations, because you'll have two, since there are two channels for the coaxial injector, that would introduce 2n more wave equations coupling in. So it can get complicated, but modern computations allow us to do that. So now let's look at the Finescale, which has to do with the injector. We have an energy equation, unsteady. We'll use turbulent heat conduction, but turbulent heat transfer. This is essentially a conductive turn, convective. In the unsteady equation, pressure comes in, and this is the rate at which energy is released due to combustion. We also have to account for the mass fraction of fuel and the mass fraction of oxygen. We bring in a system of equations that do that. Y sub I could mean Y sub F or Y sub O. There's a chemical reaction rate for each component. There's a mass diffusion that occurs, again, governed by turbulence. And it's convenient to maneuver these, create new variables, kappa, alpha, beta, to simplify the system. But the reaction rate essentially depends on the concentration through the mass fraction of oxygen, mass fraction of fuel, and exponentially depends on the temperature. And this gets spelled out a little more. And these are equations that basically bring in the momentum effects for each of these. Basically, this is a grid around each of these injectors, and we're solving well, we showed you momentum equation and the species continuity equation, we showed you the energy equation and the species continuity on the previous slide. We couple in the momentum, and actually we develop more equations from this, and I'm not going to go into all the details of the equation, but there's a standard system of equations we're solving for this on the scale. Now, here, just to test our behavior, this is an uncoupled calculation for an injector. We impose an oscillatory pressure at a certain frequency here, sinusoidal, and through the equations for the particular injector, we calculate the heat release. We do this at various points in parameter space. And if you look closely, there's a slight lag between the heat release and the pressure. You have to look carefully at it. And we're essentially trying to calculate the E term that would appear in the wave equation from this uncoupled calculation. Now, there are two characteristic times in the combustion and mixing problem. One has to do with the turbulent mixing, and that characteristic time we call tau sub m. And then one for chemical kinetics, tau sub r. And we do this for various configurations, various frequencies, and we show using color contour the magnitude of E. This is the highest region for E down here, and it gets less there. Now, for the actual case we're calculating, when we normalize tau sub r and tau sub m by the period of oscillation, or effectively multiplied by frequency, we're really moving along this path. And we see that that's passing through the most, in some of the most intense regions for the situations we're considering. So it indicates that this mechanism can be producing energetic feedback under oscillation. Now let's go to the coupling. Well, here, now we have the full chamber coupled in with the injector. And down here on the x ordinate, we're plotting the magnitude of the pulse that disturbs it. And over here, we're plotting the amplitude of the oscillation after 12 cycles of oscillation. And what you see down here for low amplitude disturbances, we originally, along this 45-degree line, that's the original state after we pulsed it, it's decaying, okay, after 12 cycles, and decaying more slowly as you get towards this boundary. Once you go above this threshold of roughly 20 atmospheres, it grows, and it always grows to about 150 something atmospheres. This is essentially a stable limit cycle. This is an unstable limit cycle over here, this magnitude. Now, if we let these calculations go longer, they will reach this. These are all after 12. I have to put it over here, right? I guess. No, I'm going the wrong way. Let's see. Somehow I lost it here. There it is. Okay, I'm sorry. So this clearly, this is all for one particular mixture ratio, one particular pressure level, etc. Just depends on how much you pulse it. If you did a different kind of so-called steady state operation, you would get something else. And this shows some of the concepts. Here we're plotting in a typical phase diagram. It's not shown here, but this is, well, shown over here. The time derivative of pressure at some point on the wall versus the pressure. We have different situations up here. We're perturbing it at a larger magnitude than the stable limit cycle. It decays to the stable limit cycle. Down here, this is a blow up of this region. This is all in this area. Here, it's just decays with time. And over here, we're above the threshold here, a different scale again, and it grows to the stable limit cycle, consistent with before. These are two examples of a spinning wave with different initial pulses, 9.5 atmospheres and 30. Remember, 20 was the triggering point. This one, if you look at these numbers, is getting lower in time. Of course, it's looping, but generally it's getting smaller in time, and here it's getting bigger in time. This is going unstable, consistent with what we showed before. This now shows that we're changing the operating conditions, mixture ratio, and injector velocity. Could change a lot of things, but these are two things we're changing. In this zone up here, it's unconditionally unstable up here. Out here where the red is, it's unconditionally stable, always decays. In between, with the right threshold, exceeding the right threshold, you grow to a stable limit cycle. If you come over here and plot, now, basically this now is going up here, right? And what it shows is that up here, the high injector velocity, you're in this region along here. Over here, where it'll grow to some limit cycle, you're in this region with the blue, and then the red is actually out here on this to the left. Okay, so this is looking at a cut, so to speak. Now we go along this line here, changing mixture ratio at a fixed injector velocity, and this is all unconditionally, conditionally unstable. And what you see is that you always, in this domain, have some threshold, and you will then grow to the stable limit cycle if you exceed this. But to the right or to the left, you will be stable. Okay, so that shows the consistency. Now, there was no detailed experiment for cylindrical chamber, and that's the norm for design. Maybe something like a slightly truncated cone, but close to a cylinder is the norm. But there's an experiment at Purdue University where they built a rectangular chamber combustor in order to give them better access. I really skipped a few there, didn't I? Give them better access to viewing. They were doing not just pressure measurements, but viewing OH radicals. So this is essentially half of that, as if you put the mirror image on top of it. And they reported certain data depending on, they have 7 injectors. These are the coaxial injectors cut in half with fuel and oxidizer. And there are 4 different cases we compared. The solid lines are their experimental results because they didn't perturb it. The O means the injector was flowing both fuel and oxidizer. The X's mean that it was flowing just fuel without oxidizer. So they did different combinations of this, and basically putting the fuel and oxidizer in the combustion closer to the outer sides makes it more unstable. So they got different amplitudes depending on what configuration they used. Now, we found that consistent with what they were showing, we perturbed at different levels. The dots are our computational results. And we came pretty close to matching their experimental results, which is good. There was one point where we essentially, and this was just the only point, where they found an instability and we predicted stability at this point. So, but it was already on the margin. So we consider this pretty good. Okay, now this is again a tangent. This is now the second tangential mode. It shows an oscillation with pressure, and you see it going around. But now you see 2 peaks and 2 minimums. It's a second tangential, and if you this shows the magnitude of the heat release due to combustion. And you can, if you follow the high pressure sides around and look carefully, you see that the peaks here are occurring slightly lagged behind the peaks here. Okay, and this is just blowing up in the third direction examination of the behavior near a coaxial injector. All right, now I want to get to the stochastics and explain a little bit about it. We could do Monte Carlo calculations, which means that every realization has to be dealt with, but that would become very, very costly. So what we've done is we've found in the literature, and Finescale was especially helpful here, there's a technique which has been used in many fields, including turbulence, called the Polynomial Chaos Expansion method. And the method basically takes, you define your random variables, which in the case I'm going to show you were 5 variables that describe the triggering pulse, the magnitude of the pulse, the duration of the pulse, and it's an oscillatory pulse, so the frequency and duration affect the number of cycles it goes through. It can have an orientation if it's a dipole, which is what we're considering. You won't get a spinning wave unless you put an orientation into your pulse. So we use dipoles, for example. And the other thing is location. Where's the pulse occur in your chamber? So we had up to 5 random variables. And what you do is look for the solution in terms of polynomials, in particular the Legendre polynomials of the random variables. And what this means is that when you use that expansion, you're not solving for every realization. You actually create more equations because you have more coefficients, but you have far fewer realizations. You just have one realization. So you end up with a lot fewer equations, a lot lower cost. You're solving for coefficients in an expansion of Legendre polynomials. The Legendre polynomials are the logical choice when you say your random variables have a uniform value over a finite variation in the variable. They have a uniform probability over a finite variation in their property. If you wanted to assume a Gaussian distribution for the random variables, you should use Hermite polynomials instead. But we're working with Legendre. and assuming the flat PDF, essentially, for the random variable occurrence. Now, to put it in mathematical terms, we have a multi-scale problem. N are the variables on the chamber scale, the actual physical variables, pressure, velocity, etc. R and theta and time are the coordinates. M are on the injector scale, and X and eta and T are the physical and time variables there. C is a vector of the random variables. Let's say up to 5 is what we've done. And what you'll see is that through this is essentially schematically showing you what we're doing. Through the coupling, there's a forcing. The M again are from the injectors. They affect the chamber, and the N here come down and affect the injectors. And then N and M, as I said before, are expanded in polynomials, psi sub k, which are the Legendre polynomials. So when you put them into the equations and you take the dot product, here you're essentially eliminating the Legendre polynomials, and you're getting the equations for the coefficients. So that's the scheme which was established by others, and we're following. Okay. I think I've explained all this. Well, let's see, some of this. We examined Gaussian pulses and also oscillating diode pulses, and both have orientations. And we're going to present results in terms of a marginal probability, which means we will integrate over several of the random variables and produce results in terms of other variables. This now just shows you there are actually 3 results here. 2 different cases, one where it grew, one where it decayed. We're plotting pressure versus time at some point. And what we're doing is, one is the exact simulation, just straight old-fashioned CFD. And then the reddish color is the Legendre polynomial to 6th degree, Polynomial Chaos Expansion, and then to 7th degree. Okay? So basically our conclusion is that 6 and 7 degrees get us where we want to go, right, in terms of this. You have to truncate your polynomial somewhere, and so we're trying to find out what's good enough. Now, we did do Monte Carlo calculations and use theory with 10,000 samples too. This is now the error expected from the stochastics and the computational cost. These are both log plots, right? So the difference is big. We took 7th degree as exact. 7th degree polynomial is exact in measuring this. But what you see is that you can get down below 1% error here, and the polynomial chaos is 2 orders of magnitude less expensive. Okay, so that shows why we're doing it. We can run a lot more cases that way. Now, I mentioned that we, okay, I think I'll get there. This is the marginal probability. We have 5 random variables, but we're integrating over 4 of them and just plotting versus the dipole magnitude. This is the probability of growth. As you would expect, it grows, but reaches a finite, a constant limit, asymptote. And of course, it's less than 1, 0.3, down to 0. And these bars are what we would, oops, I went the wrong way. The bars are what we would get from the Monte Carlo with 95% confidence. So there's pretty good agreement in the few cases that we did the Monte Carlo. This is the period ratio of the dipole oscillation to the first tangential mode. Obviously, you're more likely to trigger an instability, again, marginal probability, when they're matching here at 1. And again, the Monte Carlo agreement is pretty good. Here is the radiolocation of where the disturbance occurred. And as one would expect physically, if the location is near the outer radius, 14 centimeters is the radius of the chamber, the closer you get to that, the more probable you will get a drive and instability. The reason being is the pressure amplitude is for the first tangential mode is largest at the outer radius. It's continuous and goes through 0 at the center. Another one is how are you orienting the dipole? And essentially what it shows is if you orient it radially, you get the least probability. If you orient it tangentially in either direction, you're more probable to get a spinning mode. So orientation is a factor there. This just takes the marginal probability by integrating over 3 of the 5 random variables, and so we can plot against 2 of them. For example, orientation and the period ratio over here, and everything you see here is consistent with what we showed before. This now, okay, so we focused on 3 kinds of disturbances. One, which I've shown you the results for, was trying to simulate some disturbance to the flow process or the combustion process in the combustion chamber. And we use dipoles and other kinds of disturbances to represent that. Now we're going to talk about something happening upstream in the injector where there's a temporary blockage to the flow in one of the injectors. And for that, we have to analyze the injector flow. We have wave equations for the injector, which we bring in. But essentially, the combustion chamber is off to your right here. And this is the injector with fuel flowing on the outside, coming in here and in here, axisymmetric, and oxygen flowing through the inside. So we have one of these wave equations for each of these. But what we do is block one of these. I think we're doing the oxygen here. Temporarily, we reduce the mass flow coming through in some way for some time, okay, in a pulsed fashion. And what we find, and this is a stochastic simulation, this is a probability of growth where we're actually looking at different injector lengths here, 2 different injectors, but looking at various things. This is the time scale of the injector blockage, tau sub b, to the oscillation time, and if it's coordinated with the natural frequency of oscillation, it becomes more probable to have an instability. Over here, we're looking at the magnitude of the decrease in the oxygen flow rate due to the blockage, and obviously the more you block it, the more probable an instability, bigger jam, so to speak. Now, another thing we looked at, and this was new, others hadn't thought of this, had to do with acceleration or vibration of the whole rocket motor. Those of you who have studied mechanics know that there's something called a Newtonian frame of reference in which Newton's laws apply. Well, if the rocket is moving at constant velocity, we can say that a point fixed to the rocket engine could be the origin of a Newtonian frame of reference. But if there are vibrations in that engine, and I'm talking about solid body vibrations of the whole engine, which are probable in flight, that then, when you go to take your coordinate fixed to the rocket engine, it's no longer a Newtonian frame. In your momentum equations, you have to put in what I would call a reverse D'Alembert force, which essentially is driving it. The reason we thought of this was that it was observed that some engines were perfectly fine on testing on test stands on the ground, but they seemed to develop problems in flight. And one possibility is that the vibration in flight is causing that. We haven't proved that it's vibration. What we have proved is that vibration can cause can trigger an instability. And these are somehow my thumb is too big. I'm not going to do anything about that. It's going to stay just as big as it is, but let's see. I want to get to this one. Okay. So here, for example, the frequency of the vibration, if it matches the natural frequency of the first tangential is around 2,000. Obviously, it's going to be more unstable. And if you increase the acceleration, the maximum acceleration, you get a larger increasing probability of triggering the instability. So those were fairly novel results. Now, what we showed next was that anything that causes, by triggering an instability, could, when properly administered, provide a control mechanism. What made me think of this was that we know that if you have a loudspeaker over here, you can put a loudspeaker over there that's out of phase and cancel the noise. Now, we're working with nonlinear, much more than a loudspeaker. This would deafen you if you were close to these 100+ atmosphere oscillations, but it's the same concept. So we did some testing. We call it the Antipulse. And this one, we did it various ways: acceleration, injector blockage, the dipole pulsing. All of them produced equivalent results. But what you would see is, suppose you were in a domain where an instability was growing, like this. If you administered an antipulse quickly enough, proper phasing, you could cause it to decay, the green line. If you waited a little longer, you could cause it to decay, but then it would grow again. If you waited still longer, there would be some decay, but then it would start to grow. But if you pulse it again, this is a 2-pulse one, you could then bring it back. So the idea of multi-pulsing. So you can think of control mechanisms where you could deliberately block the injector flow, or deliberately create a vibration that might lead to a control mechanism. We haven't fully explored this yet. I'll be very fast and try and close. We did some perturbation analysis, which meant not CFD, and showed that the amplitude of the first tangential wave A, we went to third order in a perturbation analysis to get the nonlinear terms. We showed that it could behave like this, and the phase of the oscillation could also depend on the amplitude. And actually you can get exact solutions to this. And what it shows is that for this case, that if this is essentially the threshold for A. If you disturb it below this, you decay. If you disturb it above it, you grow. We'd have to carry it higher order in the perturbation in order to get the stable limit cycle to which this grows. Here with the perturbation analysis, we went from 10 injectors to 19, and we first added them. Well, the total mass flow stays the same as we add injectors. So each mass flow gets less mass flowing through it than it did before, but the sum is the same. As we add them first in the interior ring, we add 3 to the 3 that were there before, we become actually more stable. The A here moves up, the threshold moves up. But then we start adding to the 6 that are in the outer ring, which brings more mass flow closer to the outside, and we bring it down. So it becomes at the end even more unstable with a lower A. Here's something we just presented a few weeks ago at an AIAA meeting. This has to do with events. We were looking at pulses which were relatively short in duration. Suppose you had a lot of noise for a long time. Could it possibly lead to slowly pushing you above the threshold? And the answer is yes, it could. And actually, this was Pavel Popov's idea, my postdoc, and he pursued it. And what we basically, there is a theory that exists. We used acceleration, but you could use anything. You could take a smaller, we would need millions of samples for the case we were looking at, but there's a possibility using something called an importance ratio, where if this is the actual distribution of the noise amplitudes, exponential and amplitude A, where the offset is 0, the mean is 0 here, by properly changing the mean to some selected value, you can make the instability more probable, but then this ratio here becomes an importance ratio, and you use this to get the probability of the real sample at the end. So basically, through this established technique, you're able to create a smaller sample where the probability of an instability is greater, and then after that, through the use of this importance ratio, go back and say what it actually would be in the realistic sample. And you're able at low cost then to predict low probability events. All right, so we think we've demonstrated the ability to predict combustion instability with a nonlinear wave dynamics model coupled with the injector. We've predicted transverse cylindrical chamber waves, and we also, for the purpose of comparing with the experiment, went to a transverse rectangular chamber. We predicted the 3 different modes: unconditionally stable, unconditionally unstable, and bistable or triggered operational domains. And we agreed with the experiment at Purdue, and we identified several mechanisms, one new, the acceleration, and identified potential pathways for control with the anti-pulsing. We used, was new for us, and reasonably new in the field too, Polynomial Chaos Expansion, but we certainly weren't the first to do it. And we were able, by a stochastic approach, to predict probability of triggering mechanisms if we have a good handle on the probability of the random events. We've increased computational efficiency and improved efficiency of basically by a combination of things, reducing dimension, for example, and through the PCE approach. So thank you very much. I hope I stayed on time.
Questions? Questions to Dr. Sirignano?
Yes.
You talked a little bit about antipulsing, and you said that you guys haven't done too much into it yet, but from a practical standpoint, what sort of sensors could be implemented with enough fidelity to actually respond?
Obviously, you'd have to sense it, but well,
Sirignano, if you can repeat the question so that they can hear it live broadcast.
The question concerned the potential for the anti-pulses as a control mechanism, and in particular, what kind of sensing one would need. Obviously, it's a good question because you would have to have a sensing monitoring mechanism in order to know when to exercise, that is, create the anti-pulse. Well, the easiest thing to measure in these high temperature environments is pressure at the wall, okay? So that would be the first thing that people would look at, and actually that's what is done in experiments. Pressure measurements are made at different points so that you not only can tell the amplitude and the frequency of the oscillation, but by having it at different points and looking at the phase, you can tell what kind of mode you have. Is it oscillating in the longitudinal direction? If you have pressure sensors at different longitudinal locations, in the azimuthal direction, if your sensors are active, and is it a standing wave in the azimuthal direction, or is it what we call a spinning or traveling wave? These can be determined, and then once you have that, in principle, you can have the microprocessors that would exercise whatever control you want. But again, we haven't gone, I didn't want to give the impression that we're developing control mechanisms. We just wanted to show the plausibility of these mechanisms. The bad things that could happen could also, in a controlled way, do some good things. That's the point.
Other questions? I have a question.
Sure.
For the pressure wave equation, do you solve coupled with your flow equation, or do you do iteration? I mean the wave equation.
Well, it's a partial differential equation, a system of partial differential equations, and what we do is use finite difference.
Are you coupled with your flow field? Are you coupled with your flow field, or you solve it separately?
Coupled with what?
With the flows, with the flow field.
No, okay, these, we have the momentum equations and the wave equation. The energy equation for the wave dynamics has already been coupled into the relationship between density and pressure. So it's already been factored into those equations. What we're doing is solving at the chamber, those system equations simultaneously, in time, but also coupling them, one term in the wave dynamics equation, the energy release term, or sometimes I called it the heat release on the slides. That E comes from the analysis of each of the local grids around the injectors. And so those equations are coupled in to provide the E, but the pressure and velocity oscillations in the chamber affect the mixing and combustion rate in the injector zone as well. So there's two-way coupling between the wave dynamics and each of the injectors. Each of the injectors is uncoupled from the other injectors directly. All right. Okay. So we don't have two flames from different injectors overlapping. Okay. In our model. Yeah.
More questions?
Dan.
Do you work with the designers? And if so, how does that work?
With designers?
Yeah.
Well, we're not with per se designers. We are in contact with the Air Force research labs at Edwards Air Force Base, and they're interested in advancing the technology, talking more about engines that might be built than engines that are being built. Most of the interesting things in the newspapers with rocket engines are actually being done with 1970, 1980 technology. Okay, so people are talking now of going to higher pressures and doing lots of other things that, and there's not a major design project underway, but hopefully there will be. So.
Okay, I think if no more questions, we'll conclude here.
Thank you.
Sirignano, our dean has a small gift for you. And this is a hat.
Oh, good.
Stand for UN.
Oh, well, good.
And there's also a small gift here.
Well, thank you very much. Thank you.
Thank you for coming.